Hey everyone, and welcome to This Explainer. I am absolutely thrilled you're here today because we are going to unlock the secret, everyday language of chemistry. We're not just going to sit here and memorize dry textbook rules, right? We're going to actually learn how to read the hidden code of the universe that's happening all around us every single second of the day. So grab your virtual lab goggles, get comfortable, and let's dive right in. Okay, let's start by picturing a few totally relatable daily phenomena. Think about what happens when milk is just left out on the kitchen counter during a really hot summer day. Or imagine an iron pan you accidentally left outside in the humid rain. What actually happens to them? Well, the milk goes all sour and clumpy, and the iron pan gets totally covered in that crumbly reddish-brown rust. In both of these situations, the core nature and the identity of the initial substance have completely changed. It's not just a simple physical shift. A whole new substance has literally been born. And whenever a change exactly like that occurs, we can confidently say that a chemical reaction has taken place. So here is our quick roadmap for today. Number 1, identifying reactions. Number 2, writing and balancing equations. Number 3, combination reactions explained. Number 4, decomposition reactions explained. And finally, a fun student Q&A challenge to test what we've learned. All right, section 1, identifying chemical reactions. Let's get right into that lab mindset. We know that chemical reactions happen when substances change their fundamental identity, but how do scientists actually spot these changes in real life? You don't always need complex million-dollar microscopic equipment. You really just need to know what physical clues to look for. And there are 4 major physical clues that practically scream, hey, a chemical reaction just happened. If you mix 2 things together and they suddenly change state, change color, start bubbling and evolving a gas, or if the container itself suddenly gets hot or cold to the touch, well, you are witnessing chemistry in action. Now, when making these observations in a real-world setting, safety is absolutely paramount. You never ever just stick your nose directly into a test tube. Instead, you gently waft the air towards you, and you always handle materials carefully, using tongs and the proper safety gear. Observing safely is what allows us to gather the physical evidence we need to actually prove a chemical change has occurred. Moving right along to section 2, writing and balancing equations. Now that we know how to spot a reaction, we run into a bit of a practical problem. Describing these reactions in full sentences, it just takes way too long. We need a faster way to communicate. Say we burn a magnesium ribbon. We could write out the long word equation, magnesium plus oxygen, and then draw an arrow pointing to magnesium oxide. I mean, it works, but it's super clunky. Contrast that with the sleek, concise chemical equation right below it. Mg plus O2 yields MgO. This right here is exactly why scientists prefer symbols. It's basically a mathematical shorthand that tells you exactly what elements are involved in the reaction. The substances going in on the left are our reactants, and the brand new substance on the right is our product. But here is where we hit a golden rule. It is absolutely crucial we understand the law of conservation of mass. In plain English, this just means the universe doesn't do magic tricks. Mass can neither be created nor destroyed in a chemical reaction. So whatever number of atoms go into the reaction as reactants, that exact same number of atoms must come out as products. You can't just lose an oxygen atom into thin air, right? This absolute, unbreakable rule is exactly why balancing our chemical equations is completely mandatory. Let's look at a totally unbalanced or skeletal equation using the hit and trial method. Imagine iron reacting with water to form iron oxide and hydrogen gas. If we tally up the numbers, we put in 1 iron atom on the left side, but somehow got 3 out on the right. We put in 1 oxygen atom, but got 4 out. The mass is clearly not the same on both sides, which means we've got some balancing to do. So let's build this into a totally foolproof process. Step 1 is literally the most important part. Draw boxes around each chemical formula. Why? Because you must never ever change anything inside those boxes. You can't just change H2O into H2O2 to make the math work out. That changes everyday water into hydrogen peroxide, which is a completely different chemical. Step 2 is to list your atoms just like we did a moment ago. And step 3, start balancing by adding whole numbers or coefficients in front of the boxes. A pro tip is to usually start with a compound that has the most atoms. After multiplying our molecules to get the counts to perfectly match, we arrive right here at our beautifully balanced equation. We now have 3 irons, 8 hydrogens, and 4 oxygens on both sides. Perfect. And hey, take a look at those little letters in the brackets, the S and the G. These act as brilliant little cheat codes for the physical states. S means solid, G means gas, L means liquid, and aqueous means aqueous, which just means dissolved in water. So now our equation isn't just balanced, it tells us the entire story of the reaction's physical state. Awesome! Section 3, Combination Reactions Explained. All right, so we've mastered the language itself. Now let's look at the actual conversations happening between these elements. First up is the combination reaction. Let's completely de-jargonize this term. A combination reaction is quite simply taking two or more distinct ingredients and mashing them together to bake one brand new cake. Two or more reactants combine to form a single unified product. Simple as that. And you see this happening everywhere in daily life. Burning coal is a classic combination reaction where solid carbon combines with oxygen gas to form a single product, carbon dioxide. Hydrogen and oxygen gas combine to form water. But here is actually my favorite practical example, whitewashing walls. When you mix quicklime, which is calcium oxide, with water, they combine vigorously to form a single product called slaked lime, or calcium hydroxide. That slaked lime is then applied to walls, where it slowly reacts with the air to create a beautiful, hard, shiny finish. Now, if you actually mix that quicklime in water yourself, you would definitely notice the container getting incredibly hot. That's because it is an exothermic reaction. Exo means out, and thermic means heat. So these reactions actively released heat along with their products. A brilliant everyday example of an exothermic reaction is actually happening inside of you right now. As your body breaks down carbohydrates into glucose, that glucose combines with oxygen in your cells to provide you with energy. Respiration is literally a controlled chemical fire keeping you alive. How cool is that? Okay, Section 4, Decomposition Reactions Explained. Let's shift gears completely and explore the exact opposite mechanism. If combination reactions are all about building things up, what happens when we want to tear them down? Well, that brings us to the decomposition reaction. In a decomposition reaction, a single complex reactant breaks down to give multiple simpler products. Think of it kind of like taking a massive complex Lego spaceship and shattering it down into its individual, simpler Lego blocks. But here's the thing. Chemicals don't usually just fall apart on their own. They need a little push. Scientists use different energy tools as triggers to forcefully break a chemical apart. For example, we can use intense heat, like baking limestone until it breaks down into quicklime for manufacturing cement. We can use sunlight. Leaving white silver chloride in the sun causes it to decompose into gray silver metal, a process that was historically used in black and white photography. Or we can even use electricity, literally zapping water to forcefully split it back into pure hydrogen and oxygen gases. And finally, Section 5, the Student Q&A Challenge. Okay, we have covered a massive amount of ground today. You've learned how to identify, write, balance, and categorize these chemical reactions. Now it's time to hype up those brain cells a bit. Here is your first textbook mystery, derived straight from the source material. Why should a magnesium ribbon be cleaned with sandpaper before burning it in the air? I'll give you just a second to formulate your own answer based on what we've learned about how chemicals interact. And the answer is to remove any protective layers or impurities. Magnesium is a highly reactive metal, and over time it forms this dull layer of magnesium oxide on its surface just from sitting around in the air. If you don't scrub that off with sandpaper, the pure magnesium inside can't make direct physical contact with the oxygen in the flame. So if you guess that reactions require direct pure contact, your logical thinking is spot on. All right, let's hit challenge 2. Remember a minute ago when we talked about using electricity to zap water apart? That process called electrolysis? Well, when scientists collect the two gases that bubble up in separate test tubes, they notice something super weird. The amount of gas collected in one tube is exactly double the amount collected in the other. Any ideas why? The super satisfying answer is actually hidden in plain sight within the world's most famous chemical formula, H2O. Because every single water molecule naturally contains 2 atoms of hydrogen for every 1 atom of oxygen, when you shatter that molecule apart, you are inherently going to get twice as much hydrogen gas as oxygen gas. It's the law of conservation of mass proving itself right before your very eyes. And that perfectly wraps up our journey today. But I do want to leave you with one final fun challenge. Look around your home right now. Is there a rusted nail somewhere? Is someone cooking dinner in the kitchen? Are you simply sitting there breathing? I challenge you to look at your everyday world through the eyes of a master chemist. What hidden chemical reactions are happening right in front of you right now? And how would you go about balancing their equations? Keep observing, keep questioning everything, and I will catch you in the next explainer.